My name is Camilla, and thank you all for coming. So, as the title says, the title of my talk is A Tube Story, which is a nod to the classic 1970s film, A Love Story, which I haven't seen, but people tell me it's about two people who love each other very much. So this talk is going to be about my love for the London Underground. Right. So, roughly, I'm going to divide this talk into three parts. The first part is going to be a bit about my motivation. So why would you want to study the London Underground? And what kind of questions might you want to answer? What kind of questions might you want to ask about the London Underground? In the second part, I'm going to talk about GraphTool, which is a Python library that allows you to analyze graphs. And then in the third part, I'm going to talk a bit about SimPy, which is a simulation library that you can use to create various kinds of simulations. For example, simulations of the London Underground. Right. And just a note before we start, SimPy should not be confused with SimPy, which confusingly sounds exactly the same. But SimPy with a Y is a symbolic computation library, whereas SimPy with an I is a simulation library. And someone on the internet told me that you should actually pronounce SimPy, the simulation library, as SimPy, but I won't be able to do that with a straight face. So I hope no one minds. I'll keep calling it SimPy. I'm not going to say SimPy. That's just ridiculous. I'm sorry to whoever came up with that name. Okay, so before we dive into the talk, just a little bit about my background. So I graduated in 2013 from a small university just outside Philadelphia. And I spent a year at Edinburgh, mostly wearing a lot of heavy rain gear, but also sometimes writing some Python. And after that, I moved to London and took up a job as a data plumber, which basically means I move data and create some minor disasters occasionally. Right. So my story really starts in August 2014 when I first moved to London. And my first home was located somewhere around near Edgware Road, and my job was located at Liverpool Street. So here I was, this was my first day, and having lived in Edinburgh for a year, I was really unprepared for the challenges of commuting in a large city. So I thought, okay, at 8 a.m. I'll just go to the Edgware Road station, and I'll catch the Circle line, and everything's going to be fine. So this is how I thought it would look, a few people, it's going to be okay. So here I go. I arrive at Edgware Road at 8 a.m. and I quickly realized that one does not simply board the train at 8 a.m. In fact, I had to let around 6 trains go before I could finally squeeze myself into the 7th one. It was not a very pleasant experience, and I was almost late for my first day at work, which also is not a very pleasant experience. Right. But, after a few weeks, my tube savvy level, gets up. So as the number of commutes rises, so does your number of commuting hacks that you acquire. So these are basically helpful rules that will help you navigate the London Underground in the most efficient manner. For example, my top 3 rules for the first month is board at Edgware Road before 7:30. This will guarantee you a place on the tube without having to feel like a sardine. The second one, which I had to learn the hard way twice, never attempt to board anything at Victoria because it will never happen, ever. And then if you come to the station and you see that funky looking table with all those severe delays, you might as well just go back to sleep because it ain't gonna happen. Right. So these rules were fairly successful at, getting me to work on time, but I realized that sometimes they didn't work because actually the flow of commuters on the London Underground can behave quite erratically depending on what's going on. So some days I would come to Edgware Road a bit late, so I'd come at 8, and all of a sudden I was expecting to see this huge crowd, but then there is no one, and I'm standing there and I'm thinking, okay, is this a bank holiday? I'm actually supposed to be still in bed? Or did the ticket barrier accidentally teleport me to an alternative universe? Then on some other days, I come to Edgware Road at 7:30 and there's a ton of people and I'm like, okay, what is going on? So it seems to me that sometimes on the tube network, you can have distant signal failures or congestions on distant lines that can then ripple throughout the network because people are routed from one particular section of the network to another, and thus, even though your particular area of the underground network is working well, the extra pressure from all the commuters coming from other parts of the network that aren't functioning very well can cause congestion. In fact, this has already been studied quite well by professors around the world. And if you're interested to learn about the flow patterns in commuter networks in urban transportation, you can read this excellent book by Professor Sheffy from MIT. I've linked to it from the slide. So what Professor Sheffy writes is that the flow pattern in an urban transportation network basically depends on two competing mechanisms. So first of all, there are the users. There are the very stressed London commuters that want to get to work as fast as possible. And a user always strives to minimize the cost of their travel. So this is not necessarily the cost of your Oyster card or your pay-as-you-go, as the fashionable people do it nowadays, but this can be pretty much anything. This can be your time taken to travel from point A to point B, or for example, how frustrating it is or how many times you have to change train. So cost can be measured in a variety of different ways. Now, if cost of traveling would stay constant throughout the day, it would be quite easy for every user to optimize their path. Unfortunately, the second competing mechanism that determines these flow patterns is basically the change in the cost of travel according to the load. And anyone who's commuted at 8 a.m. or at 5 p.m. knows what I'm talking about. Commuting during rush hour is significantly more stressful than commuting at, let's say, 2 p.m. when there is no one. So keeping this in mind, I came up with two questions that I wanted to answer. So I wanted to know, what are the most important stations on the underground? So what are the key critical stations where if a disruption were to occur, you would pretty much screw up everybody's commute? And secondly, I wanted to sort of start quantifying how disruption at these stations would affect the rest of the network. And this is basically what I'll be talking about in part 2 and part 3 of the talk. So in part 2, I'm going to use GraphTool, which is an excellent Python library to perform some static graph analysis on the London Underground network. Before we can do that, however, we need to collect some data. So I am an extremely lazy data plumber, and here is my life pro tip. Do not reinvent the data file, use Google. So in this case, I tried to Google for a convenient data file where someone would have basically defined every single station on the London Underground and then somehow made it easy to parse that into Python and then generate a graph. Unfortunately, my Google foo level wasn't high enough, so I was not able to find this file. Instead, I had to make a strong cup of coffee and write it myself. So basically, this is what the file looks like. For every single of the almost 300 stations on the Underground, you basically define the station, you define its neighbors, and then the two blinds that go to those neighbors. And I just realized that I misspelled Piccadilly line. I apologize to any Piccadilly line fans, this was not intentional. It's a difficult word. Anyway, so this is what my data file looks like. And you can then write some simple Python functions to parse this into a graph object. So let's start by examining some GraphTool basics. So first of all, if we want to create a graph, we need to create a blank graph object. And this is done quite simply by calling the graph constructor, as you can see. Do we have a pointer?
No.
Okay, you're just going to have to imagine me pointing at that box. Anyway, so we have a blank graph object, and then we can add some vertices to that graph by calling, surprise, you guessed it, add vertex, right there. And you also want to add some edges. So this kind of very simple setup works well for small graphs, but then for large real-life applications, you also want to create something called a property map. For example, in my case, I wanted to associate the names of the stations with the vertices that represented them, and I wanted to associate the names of the two blinds with the edges that represented them. So GraphTool provides a very convenient object for this called the property map, which you can create for either vertices or edges by calling the new vertex property function. In addition to calling the function, you also need to pass the type of the value that you will be associating. So if you want to associate names of stations with their vertices, you have to pass a string. But it can pretty much be anything. So for example, if you want to associate with each station the number of commuters that enters that station during the day, you could create a vertex property map using integers. Right, so now comes the fun part, at least for me. When you're dealing with graphs, it's always fun to draw them and visualize them, and GraphTool offers you a lot of different ways that you can do that. So the simplest one that I picked and that worked for me was the graph draw function. You simply pass your graph into it, and you can pass a bunch of other keyword arguments that define the colors of the vertices or the lengths of the edges or the positions of the vertices, and pretty much anything you want. So if you're interested in tweaking your graphs, I encourage you to look at the GraphTool documentation. It's actually pretty good. So the sort of standard graph draw works quite well for small graphs. You get these nice graphics, and it also works really well for networks that are regular in the sense that they're generated by some kind of model. For example, here is a series of graphs drawn with graph draw of the price network. So it looks quite pretty. But when you're dealing with graph data that comes from a real-life application, you really can't have nice pictures because you're going to have a lot of nodes that are going to bunch together and the edges are going to be intersecting. So how do we visualize the London Underground in an efficient manner? So we have the standard TFL map, which is more or less confusing sometimes, or helpful, depending on your visual skills, I suppose. And then we also have the geographic locations of the maps, not the maps, the stations, which I've plotted here using Bokeh, and I've colored them according to the zone. So that should look fairly familiar. After that, I tried to do some visualizations using graph draw, and I came up with less than impressive results. So visualizing messy graphs is, well, it's messy, and as you can see, you can't really tell anymore where is the Bakerloo line or the central line. It's just all one mess. Also, adding vertex labels is quite impossible for a graph of almost 300 nodes. So what can you do about this? One strategy is to try out some different layout algorithms, and GraphTool is actually quite good. It provides you with at least 4 different layout algorithms. So SFDP, Fruchterman-Reingold, ARF, and then radial layout. And most of these are based on the idea that the objects in a graph form a physical system, and so you are trying to find the layout that basically minimizes the energy. Now, I'm not an expert in this, but you could probably tweak some parameters in the GraphTool layout algorithm that would give you nicer results, but fortunately I wasn't able to do that. But I am going to show you how you might want to go about creating such a layout. So once again, GraphTool makes it very easy. So you simply call the SFDP layout function and you pass in your graph as a parameter. And that returns to you our familiar property map object, which maps each vertex in your graph to a position that is computed by this algorithm. And then you simply pass in your position to the graph draw function using the POS keyword. So I did some experiments, and this is the London Underground visualized in more or less creative ways. I mean, they are quite pretty, but their value for the data analyst is not that great. But I'll just let you stare in awe for a few seconds. Okay, right. So I decided that the best way, at least for my project, was to simply plot the stations based on their geographic coordinates, so that I would at least know, what's going on in zone 1 and zone 2 and so forth. Okay. So in addition to making pretty pictures, which may not be so useful, we want to get some statistics. Luckily, GraphTool comes to our rescue there as well. So in order to compute the degree distribution, which is a common metric used to characterize networks, we can either call the vertex hist method in the stats module, or then we can simply iterate through all the vertices and call the outDegree method on each vertex to return the outDegree, or inDegree if that's what you want. And then this enables you to pass this list basically to pandas and plot it with Seaborn or whatever is your preferred method. So this is the outDegree distribution of the London Underground network. And as expected, most stations have a very low number of outDegree, and you can see the reason for that in this picture. Most of the stations in zone 3 to 6 belong to only one tube line, and so they'll only have, the one outDegree going northbound and one southbound, or east or west, depending on where you are. Okay, so if we go back to the two questions that I defined at the beginning, so I wanted to examine what are some of the most important nodes in the London Underground. And one way to do that is to compute a property known as centrality. And there are actually a few different flavors of this property. So one of them is betweenness centrality, and roughly speaking, it defines what fraction of all shortest paths pass through a given node. So if a station has a high betweenness centrality, this might suggest that a large number of commuters would pass through that station during a given day. So this is very easy to do using GraphTool. Anyway, I'll come back to how you do that, but in addition to betweenness centrality, we can also compute something called the closeness centrality. And you compute the closeness centrality for a node by summing it at the distance from that node to all other nodes and then taking the reciprocal of that sum. So if a node is fairly close to all other nodes in the network, then its closeness centrality will be quite high. Anyway, so you can compute betweenness quite easily. It's simply just one function call that returns to you both the vertex betweenness as a property map and the edge betweenness as a property map, and then you can pipe that into your further downstream analysis. Likewise, for closeness centrality, it's just a matter of literally calling one function, and then you're done. So how does betweenness centrality look like for the London Underground? So that the blue graph is something that I got from GraphDraw, and the size of the vertex is directly proportional to the betweenness centrality of that node. So as you can see, the nodes that are sort of the nodes that are located in Zone 1 have a high betweenness centrality, as you might expect, because Zone 1 contains stations such as Baker Street and King's Cross that are basically the intersections of, I think, 5 different tube lines. So it would make sense for a lot of commuters to go through those stations. This map is a bokeh map of the London Underground, where the shade of red that each vertex is directly proportional to its betweenness centrality. So the more red something is, the higher its value is. And as you might suspect, most of the high betweenness centrality vertices are in Zone 1, except for this little outlier right here. Can anyone guess what that station might be? It's in Zone 1 and it's on the Bakerloo line. Oh, that's quite close. It's actually Marylebone. So, Marylebone is the lonely outlier. Anyway, so when we sort the values, we see that the top stations for betweenness centrality are, as expected, Baker Street, King's Cross, and Liverpool Street. And I have to confess, Mile End is a bit weird, but it's quite far east, so I don't really see any rational, intuitive reason why it would be high on this list, but it is. So then, closeness centrality, which is, I'll remind you, basically measures how close, on average, a node is to all other nodes in the network, and the list looks quite different. So this time the top stations are Green Park, Oxford Circus, and Bond Street. You can also see that the distribution of values is different. So for between us centrality, you have quite a small number of stations that are very high on the list, and then everyone else has a really low between us centrality. Whereas for closeness centrality, you can see that most of the nodes in this image are actually very dark red. So what this might suggest is that there are very few critical stations measured by between us centrality, but actually most stations in the London Underground network are pretty close to each other. So no matter where you enter the network, you can still travel to other parts quite fast. How am I doing on time? Okay. So that's a very basic answer to what are the most important stations in the London Underground network. And the second question that I wanted to answer is, what happens if we suspend one of those stations? I mean, apart from chaos, we all know chaos is going to happen, but if we want to sort of quantify it, and to do that, we have to mask some of the stations in our network. And we're lucky in the sense that Graph2 actually provides a convenient filtering method to do this. So you can temporarily mask edges and vertices without actually removing them from the graph, which is quite convenient. You do that by creating an edge or vertex property map and simply setting true for all the vertices that you want to keep and false for all the vertices that you want masked. So this opens up an avenue to creating interactive graphics by using Graph2's filtering functions and then using Bokeh. So you'll have Bokeh on the front end, sort of driving the visualization, and you can type in the name of a station to filter out, and then that request is going to be sent to a backend where Graph2 will do some computing and update the between us values and then send them back to Bokeh. So this is what it might look like. So you can make an app with a map of the London Underground, which is colored by between us centrality to illustrate the most critical stations. And then you can have a small text box where you enter the name of the station and then it's masked as if there would be a signal failure at that station and no one could travel there. So, for example, if we remove Baker Street, we can see in the original image that all of the stations here have a fairly low between us centrality, but once you remove Baker Street, there's a lot more commuter traffic being routed to every single station right here. So that might suggest that the traffic patterns would be indeed quite different if Baker Street would be suspended for some reason. So you can also try this with MyLand, and you can see some similar effects where removing MyLand would basically put more commuter pressure on some other neighboring stations. So to summarize, Graph2 is pretty awesome. It lets you fly with fairly few lines of code. You can create and modify graphs. You can visualize them, although that's not very useful sometimes, but you know, pretty pictures are pretty pictures. You can also compute statistics and interesting metrics and filter nodes and do a lot more that I don't really have time to cover. Okay, so on we go and on to part 3. So doing static analysis of graphs is all good and well, but we also want to get into some simulations. And to do that, we need to employ SimPy. So this is an open source discrete event simulation library that was originally conceived by Klaus Müller and Tony Vigneault, and it is now in version 3.0. So there are 4 cornerstones to creating a SimPy simulation, at least a very simple one. And they are environment, resources, processes, and events. And during this talk, I'll be talking about 3 of them. So environment, resources, and processes. Right, so let's get started with the first one. So the environment is the command center of your simulation. The environment will take processes or agents that you want to simulate and then schedule and suspend them according to the logic that you code. So you simply create an environment by calling SimPy's environment constructor. Then you add some events and processes, and your sort of start button in this simulation is the run call, to which you can supply the optional keyword argument until, which basically specifies how many steps your simulation does before it stops. So So next up are processes. So if you want to be really formal, processes are the stuff that does some stuff with some other stuff in your simulation. So that's as formal as this is going to get. Anyway, if you want to be a bit less formal, they are Python generator functions that alternate between an active and a passive state. And unfortunately, I don't have time to talk about generators. They absolutely rock. But I've linked this talk, which is from PyCon 2014, and it is quite mind-blowing, so I do recommend watching it. So if you want to create a simple simulation of the London Underground, we might want to create a train process. So let's create a simple train process that is going to travel between stations for 3 time units and then spend 4 time units on the platform boarding commuters. So here is the high-level overview of how that's going to happen. So you're going to import SimPy, you're going to create a generator function, which is going to be your process, and then you're going to do some other magic to get the simulation started. And I'll go through this in detail. So first of all, we're creating a train process with 2 events, traveling between stations for 3 time units, and then spending 4 time units on a platform boarding commuters. So these are basically events that you yield using the yield keyword. So when this function execution hits the yield keyword, the process will be suspended. So the environment will say, okay, train, now you have to travel for 3 time units between stations before I'll resume you. And the environment will keep track of this time, and after 3 time units, it will wake up train again. So train will print arriving at station. And then it will yield another timeout event for 4 time units, which will represent the boarding of commuters. After that, you simply create the environment, you schedule the process by passing it as an argument to the process function, and then you basically just hit the start button and run the simulation, and you should get an output of something like that. So this is a very lame train. It only travels once and boards commuters once. So if you just want to take a brief step by step to how this train works. So first, the function is going to start executing. It's going to print start travel. Then it's going to yield this timeout event. So that will basically represent the time that the train spends between platforms. Then the environment is going to wake up train again. It's going to print arriving at station, and it's going to yield the timeout again, which will represent the time that it spends on the platform. So we can also make this a bit cooler by creating an infinite loop. Infinite loops are not cool, but in this case they are. So instead, you can control how much your simulation executes by passing different parameters to the until keyword. So for example, this simulation will only simulate for 30 time units before it stops, and you can see the result there. You can also go wild, and you can say, okay, let's create an underground network with 2 trains. So we're going to create an additional parameter in the function. And we're going to create 2 different trains, a circle line that travels for 1 time unit and spends 4 time units boarding commuters, and then a northern line that spends 6 time units traveling and 2 time units boarding commuters. And we pass both of these to the environment to tell the environment that, okay, these are our processes and we want you to start simulating them. So basically, you should get an output that is something like that. So that was all for processes, and next is probably the coolest thing about SimPy is resources. So what are resources? Resources are the stuff that's consumed by other stuff. So basically, space on a train, space on a platform, or available ticket barriers if we're talking about the London Underground, but really it could be anything. It could be gas pumps at a gas station, or, I don't know, chairs in a room, something like that. So there are 3 different flavors of resources, and the first one is a vanilla resource, which is basically like a gas pump at a gas station. It can be used by a limited number of processes at a time. The second one is a container type, which is a bulk resource such as gasoline. And the third one is a store, which is a more exotic resource type that can consume and produce Python objects. So previously we created 2 train processes. Now let's try to create a platform which can only be used by 1 train at a time. So how do we do this? We create a SimPy resource by calling the resource constructor. Then inside our circle train process, we create a request by calling platform request. So at this point, the train is requesting the platform for a space to approach, and we yield that request, which basically goes off into the environment and says, hey environment, this train is approaching the platform, so can it approach or does it have to wait? And after the train receives permission to approach, the environment will resume the circle train process and the train will start boarding commuters. So this is how it looks pictorially. And sort of the one thing that you have to remember is that you have to release your resources. What happens in this case when we have 1 train is that it's going to request this resource. And then it's going to arrive at the platform and start traveling again. And then at time 6, it's going to request the platform again, but it's going to stay in the limbo because you forgot to release the platform from the previous time that it arrived at the station. So this is just something to keep in mind if you start playing around with resources. So you have to always remember to release, or use a context manager if you don't trust your memory. Right, so just to summarize briefly, because I'm running out of time, SimPy has an environment which is the command center. It has processes that do things with other things, and then it has resources, which are things consumed by processes. Now, if you want to be really cool, you can bring this all together. The 3 libraries that we talked about, you can use GraphTool to compute the shortest paths for commuters entering your network. You can use SimPy to create commuter and train processes in a fashion that I just showed you. And then you can use Bokeh to visualize the results in real time. So for example, this is a screenshot from a Bokeh simulation that basically illustrates the number of commuters at each station as a function of time. So the larger the circles are, the more commuters are currently waiting for a train at that station. So you can see that it changes, and I've included a video screenshot demo if you want to see how that actually works in real time. So that was all. Thank you very much. Questions or comments are welcome, or if you just want to tell me what your favorite tube station is, that's fine as well.
Thank you, Camilla. Any questions?
Yes.
Charles?
Yeah, the last time I didn't remotely graphy, I remember using Network X, and I can't particularly remember why. Did you compare multiple? You compare that with GraphTool? Can you tell me GraphTool over Network X?
Yes, one word: speed.
Okay.
Yes. I mean, if you go to the GraphTool documentation, I mean, this might be a little bit biased because it is the GraphTool documentation, you'll see a comparison between GraphTool and Network X in terms of execution speed. And if I remember correctly, Network X is a pure Python application, but GraphTool under the hood is actually runs in C++, so speed, if that's what you care about.
Yeah, and of course it depends on what you're trying to
Exactly.
call things to run on, but fair enough.
Sure. Another question for Camilla? I have a question. So
No.
there is a game that some people play where they
I don't like where this is going.
in a 24-hour period to visit every single tube stop, right?
Yes.
Sometimes it becomes impossible because you get to choke points in the system where either it's very hard to get onto the train, it becomes slow, or the rest of it. This seems like the perfect solution to firstly working out what could possibly be the shortest time to visit every single tube stop, but also where to start, and perhaps, you know, some of the inflection points where I've got to make a chance, you know, probability between where I jump between the lines.
So that is actually an excellent question, and I have been researching this. It's called the Tube Challenge, and I think it was broken in 2011. I think the record was 8 hours. something like that. Yeah, and it was done by a guy who was a marathon runner. So when he would get to the last station in a tube line, he would run to the beginning of the other line. So you have to be quite fit. But GraphTool does include something called a traveling salesman solver, which I guess uses some heuristics to perhaps suggest an optimal path. So if you want to go down that route, then I wish you luck, and you can try GraphTool and do some data science on it.
Very good. Any more questions?
What about modifying it to, so when you use betweenness centrality, do you not actually need to have something about the distribution of where commuters actually generally travel from and to, and put that in as a weighting?
Yes, absolutely. So that's a great question, and as you know, in the mornings most people travel to London, and then in the afternoons it's reversed. So that is definitely something that you can do, and you can include weights on the vertices to help you decide that.
I have a question about the in degree and the out degree. Why you do a distinction? Because I would think about do a randomized graph.
I wanted to do a distinction because I wanted the outgoing traffic from the station to be different from the ingoing traffic. So if you have a station that has more people going out on a train, then you might want to separate it into two different edges, but you don't have to. You can do an undirected graph.
Yeah, I think the centralities you computed on undirected graph.
Yes. If that's what you can do that.
If it was got a loop anyway, so it would have to be directed, I suppose. Into the Piccadilly. Sorry.
That's okay. Random musings are welcome.
Do you have a last question for Camilla?
What's your favorite tube station?
Oh, that's a hard one. I'm probably going to have to say Marylebone because I think it's quite freaky.
Well, there you have it. Marylebone is officially the freakiest tube station to stop at. Camilla, thank you very much.
No, thank you.